Hello guys, and welcome to another video. On this video, likewise, we'll be looking at work, energy and power. So our statement reads as follows. It says we have a motor that is used to pull a crate of mass 60 kg up a 30-meter rough slope. The motor is connected to the crate with an inextensible rope of negligible mass running over a frictionless pulley. The slope is at an angle of 25 degrees to the horizontal. The crate starts from rest and reaches a speed of 7.5 meters per second at the top of the slope. The crate experiences a constant frictional force of 16.2 newtons. And then the first instruction is to define the term non-conservative force. So if we define non-conservative force, we say it is the force in which the work done on an object, or rather, let me rephrase. We say a non-conservative force is a force in which the work done in moving an object is dependent on the path taken. Okay, that is our definition. So this will be your answer, guys. Please make sure that you do write it down. That's your non-conservative force definition. Now let's look at 5.2. 5.2 says using the work energy theorem to calculate, or rather use the work energy theorem to calculate the average power that the motor must provide to pull the crate up in 2 minutes. So to answer this one, guys, the instruction is quite clear here. Let me just highlight the instruction. They are saying, okay, this is too big. Let me just put it to 50. So the instruction here is clear. They are saying we have to use the work energy theorem. So there's no other formula you should think of here. Normally they say using energy principles, but here we are supposed to use the work energy theorem. So guys, the work energy theorem is what? W net is equal to delta EK. And if we define the work energy theorem, just as a reminder, we say that the net work done on an object is equal to the change in the object's change. It's equal to the object's change in kinetic energy. And this is our work energy theorem. So work net is the sum of all the work that is done on our objects. So for us to find our work net, guys, what we are going to do is to identify the forces that are doing work on this object. The first force is the force of, since this object is on an incline, then we know that there's going to be a component force here of gravity, which is Fg parallel. But we have also been told that there's force of friction, so it's also going to be acting in the opposite direction, or force of friction. And we have the work done by the motor, and the motor is pulling this object through this rope here, right? It's just that we don't know the force that is the motor. We don't know the force, the value of the force that is getting the motor to do the work, right? But we know that the motor is doing work by pulling this object, right? So for us to find our work, we will look at the work that is done by each force here. So we have the work done firstly by the motor. The motor is getting work done by moving this object from where it's positioned up to there. So we have the work done by the motor, and we have the work done by friction, force of friction, and we have the work done by our component there, which is W. I'll say W Fg parallel, or you can just say it's the work done by gravity, and all of this is equal to delta EK. So now we are going to substitute into our formula. The work done by the motor is what we need to find first, because we know the formula for power is P is equal to W over delta T, the rate at which work is done. That's the definition of power. So this is the formula. So we need the work done by the motor. That's what we need to find the average power. So we are going to substitute here for this one, the work done by the force. We take the force of friction, the work done by the force of friction, which is 16,2 multiplied by the displacement, which is 30, and we will have cos 180 degrees. Since this is the work done by friction, that's what we are going to have. Let me just move this here. Right, guys, and then we have the work done by gravity, and the work done by gravity in this case will be the force of gravity perpendicular parallel, which is mg. Our m, which is the mass, is 60. Our g is 9,8. Then we have cos. Which angle are we supposed to use here, guys? We are going to use 180 here as well. And the reason why we are using 180, okay, there's something I forgot, very important thing before the cos. We have 60 the mass, we have 9,8, which is our g. We are going to also substitute the displacement, which is 30 degrees, and we should put sine as well, sine 25 degrees, and then we will put cos 180. And we are using cos 180 because here the FG parallel force is moving in the opposite direction of what our displacement, because it's moving downwards, or rather it's acting downwards. That's where gravity acts towards. Then we go to the other side of the equation to say equal to, we are on this side. I don't have space here, guys, that's why I've written my stuff like this. Okay, here it's 16,2, by the way, if you forgot. Then here, when we change, we are going to have our final kinetic energy. So we know that our object was initially at rest. That's what they told us here on the statement. They said the crate starts from rest and reaches a speed of 7,5 meters per second at the top of the slope. So the final velocity of this object is 7,5. So that's what I'm going to substitute for my final kinetic energy. I have half 60, then the velocity is 7,5 squared minus the initial velocity is 0, but I'm just going to substitute here. Why? I mean, not the, yeah, the initial velocity of our object is 0, so that means the initial kinetic energy will also be 0. Then from here we are going to do the math. So what we are going to do is to put all of this on the calculator. You see what I've highlighted in green? You put it on the calculator exactly the way it is. Okay, guys, so when we put all of this on the calculator the way it is, you start with this one plus this one here, the value that you are going to get. So what we'll have is the work done by the motor minus, this is the value we are getting on the left hand side. It's going to be minus 7940,999. Okay, obviously we shouldn't round off to 2 decimal places before the final answer, so the full answer is still on my calculator. I'm not gonna cancel it, it remains there, but here I'm writing it in short, and then I go to the other side. On the other side, this is what I have here. Oh, you know what, let me not round off this value here for the sake of avoiding forgetting what the value was. So I'm just gonna round it off to 4 decimal places, so it's gonna be 9861. Then I go to the other side of the equation. This is the other side of the equation, equal to, but we know this one is 0, so we focus only on this kinetic energy. And on the calculator, when I say half multiplied by 60, then 7,5 squared, the value I get is going to be 1687.5. Then from here, for me to find the work done by the motor, I'm gonna take this negative 7940,9861 to the other side. So this one I'm transposing to the other side. Therefore, the work done by the motor is going to be equal to, so what I'm saying is this 1687.5, which is still on the calculator, plus 7940,9861, and the value I get is 9628,4861, and the unit here is what? Joules. So this is my answer. This is the work done by the motor, but I'm not looking for the work done by the motor. I'm looking for average power. So once I've found that work done by the motor, what I'm going to do is to write down my formula, and the formula is P is equal to work. Well, since they said average power, we should say the formula is P average is equal to the work done by the motor divided by delta T. And our work done by the motor is this one here, which we just found, and that's 9628,4861 divided by our time. What is our time? This is our time, guys. We see that our time is in minutes, but we want our time to be in seconds. So for me to convert my time from minutes to seconds, I have to multiply by 60. If I say 2 multiplied by 60, what do I get? I should get 120. And when I find my average power, then I will say 9628,4861 divided by 120. And the answer I'm getting for my average power is 80,24 watts. That is the unit to measure power. So that's how you are supposed to approach 5.2, guys. So now we will look at 5.3. Yes. So 5.3 says, will the work done by the motor increase, decrease, or remain the same if the crate is lowered down the same slope at the same initial and final velocities? Okay, that's the question they are asking. They're asking if the work done by the motor will increase, decrease, or remain the same if the crate is lowered down the same slope at the same initial and final velocities. So this is how we should answer this question. If, guys, I'm drawing the object, or rather, let me say I'm drawing, let's say this is our object on the incline. Initially, the object was moving upwards, right? That's where the motor was pulling the object. And when the object was being pulled by the motor, there were two forces opposing the motion of this object. It was the force of gravity, which is the parallel component, and it was the force of friction. So these two forces were trying to overpower this force in terms of having this object move. But now things have changed because the object is moving now downwards. So that means we no longer necessarily have this force. We no longer have that force. And friction is no longer acting this way. It's acting elsewhere. But the force of gravity parallel is still acting this way. Fg parallel is acting now downwards, but friction is now acting in the opposite direction. So it means now this force of gravity that was working against the work done to move the object is now in favor of the object moving. Initially it was against the object moving upwards, right? But now it is in favor of the object moving downwards. So this means that when this object is moving downwards, it now has one force to fight with, whereas initially there had two forces to fight with. It was the force of gravity, parallel, and friction. But now when it's moving down, it's being assisted by the force of gravity. And the force of gravity we found, the force of gravity we found to be this one here, the gravity parallel. It was this value here, right? So this value was negative initially, but now that the object is moving downwards, it's going to be positive, right? And if it's positive and they're asking us, will the work done by the motor increase, decrease, or remain the same, then our answer will be that the work done by this motor will actually decrease. The motor won't have to now do too much work. Why is the motor not going to do too much work? It's because the motor no longer has to fight two forces that are trying to fight it from doing its work. It was two forces, that was the force of gravity parallel and the force of friction when it was moving upwards. Yeah, let me show you this diagram here. This is the one. So this is when the object is moving downwards. The motor has to fight with two objects, the force of gravity, the two forces, the force of gravity parallel and the force of friction. So there's too much work that the motor has to do, since it is fighting against two forces, right, that are opposing the motion of this object. However, when the object is now moving downwards, it is being assisted by this force of gravity parallel and is only fighting against the force of friction. So the work done by the motor will then have to decrease. It no longer has too much work because it's only fighting against one force that is opposing its motion, and it is being assisted by this force. Why is it being assisted by this force of Fg parallel? It's because this force is moving in the same direction as the motor. Okay, so that's how we should be answering this question, to say that the parallel, yeah, the reason I've given, guys, it's just that I can't put it in writing, but yeah, the reason is that the motor is now being assisted by the force of gravity parallel instead of it opposing the motion as before, along with force of friction. It is now fighting against only one force that doesn't want it to do work, which is the force of friction. Yes, that's the best way to put it. You can just try to use your own English there, but that's how we answer this question. Goodbye, guys, and see you on the next one.